Imagine a peaceful day at sea where the water stretches out endlessly, calm and serene. Beneath this tranquil surface lies a world of geological activity and mystery. Deep down, where the Earth's crust meets the ocean floor, is where the start point of ocean tsunamis begins, a place of immense power and potential chaos. To understand where tsunamis start, we first need a little geology lesson. The Earth's crust is not a single solid piece. It's made up of enormous slabs called tectonic plates. These plates float on the semi-fluid mantle beneath them and are constantly moving, albeit very slowly. They can slide past one another, collide, or move apart. This movement is often imperceptible, but can lead to dramatic geological events. Most of the world's earthquakes, and consequently tsunamis, occur at the boundaries where these tectonic plates interact. These boundaries are classified into three main types: convergent, divergent, and transform. Convergent boundaries. These occur where plates move towards each other. One plate may be forced beneath another in a process known as subduction. This is the most common cause of powerful tsunamis. Divergent boundaries. Here, plates move apart from each other. Magma from beneath the Earth's crust can rise up to fill the gap, creating new crust as it cools. While less common for tsunami generation, underwater volcanic activity at these boundaries can still cause them. Transform boundaries. These are places where plates slide horizontally past each other. While this movement can cause significant earthquakes, it's less likely to generate tsunamis compared to convergent boundaries. Subduction zones are the primary birthplaces of tsunamis. These zones are found at convergent plate boundaries, where one tectonic plate is forced beneath another into the mantle. This process doesn't happen smoothly. The plates often become stuck due to immense friction and pressure. Over time, stress builds up as the overriding plate is pulled downwards by the subducting plate. Eventually, this stress exceeds the friction holding the plates together, causing a sudden release in the form of an earthquake. The energy released during this earthquake can displace a massive volume of water, initiating a tsunami. When an underwater earthquake occurs, it's not just the shaking of the ground that matters, but the way the seafloor moves. If the earthquake causes the seafloor to uplift or drop suddenly, it displaces the overlying water column. This displacement is what generates the tsunami waves that radiate outwards from the epicenter. Let's imagine this with a simple analogy. Think of the ocean as a giant bathtub. If you were to quickly push up or down on the bottom of the tub, the water would slosh around violently. In the ocean, the scale is immensely larger, and the energy involved can move billions of tons of water. While most tsunamis are caused by underwater earthquakes, there are other natural events that can also trigger them. Volcanic eruptions and landslides, both above and below water, can displace large volumes of water and create tsunamis. Volcanic eruptions. Submarine volcanic eruptions can cause rapid displacement of water, especially if the eruption leads to a partial collapse of the volcano. For instance, the eruption of Krakatoa in 1883 caused a catastrophic tsunami that resulted in over 36,000 deaths. Landslides. Both underwater, submarine, and above-water landslides can generate tsunamis. When large amounts of rock and sediment slide into the ocean, they displace the water and create waves. An example of this is the 1958 Lituya Bay tsunami in Alaska, caused by a massive landslide, which produced a wave over 1,700 feet high. Once the initial displacement of water occurs, the tsunami wave begins its journey. This stage is known as the generation phase. The energy from the earthquake or other triggering event transfers to the water, creating waves that travel outward in all directions from the point of disturbance. In the open ocean, these waves can travel at astonishing speeds, up to 500-600 miles per hour, 800-970 kilometers per hour. Despite their speed, the waves in deep water are often only a few feet high and can be spaced hundreds of miles apart. This makes them difficult to detect without specialized equipment. To monitor and detect these deep ocean tsunamis, scientists use an array of DART, deep ocean assessment and reporting of tsunamis. Buoys. These buoys are equipped with sensors that can detect changes in water pressure caused by passing tsunami waves. The buoys transmit this data to monitoring centers, allowing for early detection and warning. Imagine a network of sentinels scattered across the ocean, each keeping watch for the subtle signs of a tsunami's passage. These buoys play a crucial role in providing early warnings, giving coastal communities valuable time to evacuate and prepare. As the tsunami travels across the open ocean, it loses very little energy. This means it can cross entire ocean basins, wreaking havoc thousands of miles from its origin. The real drama, however, begins when these waves approach the shore. In the deep ocean, the tsunami waves are long and low, but as they enter shallower waters, a process called wave shoaling occurs. The waves slow down due to the friction with the rising sea floor, but the energy remains the same, causing the waves to grow in height. Wave shoaling is like the ocean's way of saying, brace yourself. As the tsunami waves slow down, they bunch up and grow taller. This transformation can turn a seemingly harmless wave in the deep ocean into a towering wall of water near the coast. To picture this, think of a row of people running towards a narrow door. As they get closer, they slow down and bunch up together. Similarly, the tsunami waves, when they reach the continental shelf, start to slow down and pile up, resulting in a significant increase in wave height. As the tsunami waves reach the shore, they can range from a few feet to over 100 feet in height. The impact on coastal communities depends on several factors, including the shape of the coastline, the underwater topography, and the wave's energy. The first wave is not always the biggest or the most destructive. Tsunamis often come in multiple waves, known as a wave train, with each wave potentially more powerful than the last. The time between waves can range from a few minutes to over an hour. When a tsunami strikes, it can cause catastrophic flooding, sweeping away buildings, vehicles, and anything else in its path. The force of the water can uproot trees, demolish structures, and create widespread devastation. The inundation can reach several miles inland, depending on the wave's energy and the coastal geography. The aftermath of a tsunami is often a scene of utter devastation. Entire communities can be wiped out, leaving behind a landscape of debris and destruction. The immediate priority is search and rescue operations to save lives and provide medical assistance to the injured. Once the immediate crisis is over, the long and arduous process of recovery begins. This involves rebuilding homes, infrastructure, and livelihoods. Psychological support is also crucial, as survivors may be traumatized by the disaster. International aid and support play a vital role in the recovery process. The scale of destruction often requires resources beyond what a single country can provide. Relief organizations, governments, and volunteers come together to help affected communities rebuild and recover. Each tsunami event provides valuable lessons for future preparedness and mitigation. Understanding the start point of tsunamis, where and how they originate, helps scientists and authorities develop better warning systems and response strategies. Education and awareness campaigns are essential to ensure that people living in coastal areas know the risks and what to do in the event of a tsunami. Schools, communities, and governments play a key role in promoting tsunami preparedness. Advancements in technology have significantly improved our ability to detect and respond to tsunamis. Early warning systems use a combination of seismic sensors, ocean buoys, and communication networks to provide timely alerts. When an underwater earthquake is detected, seismic sensors measure its magnitude and location. If the earthquake has the potential to generate a tsunami, the information is relayed to monitoring centers. DART buoys then detect the actual tsunami waves and confirm their presence. Once a potential tsunami is confirmed, warning centers issue alerts to affected regions. These alerts can be disseminated through various channels, including sirens, text messages, radio, television, and social media. Coastal communities often have designated evacuation routes and shelters to help people move to safety quickly. Understanding the start point of tsunamis is enhanced by looking at real-world examples. Here are a few notable case studies. Indian Ocean Tsunami, 2004, One of the deadliest tsunamis in history was triggered by a massive undersea earthquake off the coast of Sumatra, Indonesia. The earthquake, with a magnitude of 9.3, caused the seafloor to uplift, displacing a huge volume of water. The resulting tsunami affected 14 countries and killed over 230,000 people. Tohoku Tsunami, 2011. A magnitude 9.0 earthquake off the coast of Japan triggered a devastating tsunami. The waves reached heights of up to 133 feet, 45 meters, and traveled up to 6 miles, 10 kilometers, inland. The disaster caused significant loss of life and damage, including a nuclear meltdown at the Fukushima Daiichi nuclear power plant. Chile Tsunami, 1960. The most powerful earthquake ever recorded, with a magnitude of 9.5, struck off the coast of Chile. The earthquake generated a tsunami that affected coastal areas in Chile and traveled across the Pacific Ocean, causing damage as far away as Hawaii, Japan, and the Philippines. While technology and early warning systems are crucial, community preparedness is equally important. Coastal communities need to have plans in place for evacuation and response. Regular drills and education programs help ensure that everyone knows what to do in the event of a tsunami. Preparedness measures can include building seawalls and other protective infrastructure, designating evacuation routes, and creating community response teams. It's also important for individuals to have emergency kits with essentials like food, water, and medical supplies. The start point of ocean tsunamis lies deep beneath the surface, in the dynamic interactions of the Earth's tectonic plates. These powerful geological forces can unleash waves of destruction that travel across entire oceans, affecting distant shores. Understanding the origins of tsunamis helps us appreciate the complex and interconnected nature of our planet. It also underscores the importance of preparedness and resilience in the face of natural disasters. As we continue to learn from past events and improve our detection and response capabilities, we can better protect ourselves and our communities from the devastating impact of tsunamis. By respecting the power of nature and being prepared, we can reduce the loss of life and damage caused by these awe-inspiring and destructive waves. Please do not forget to like and subscribe for more interesting videos.